I know. Something about, yeah. All right, so here's a scenario. Guys, you need to pay attention. You need to pay attention. This is important. I'm going to go step by step. Start basic, go complex. You've got to understand the basic, like understand the basic to get the complex. Okay. Real basic. I have a ceiling, I have a rope, and I have a box. Let's say the box weighs 10 kilograms. Okay? Let's do a free body diagram around the box. Okay? When I say we're going to do a free body diagram around the box, here's what I'm doing. I'm drawing an imaginary box around my box, or my object. I'm drawing an imaginary box around the object that's hanging from the rope. Okay? Then I'm going to do the free body diagram. I'm going to call this number 1, because we're going to do a couple of free body diagrams. Free body diagram number 1. It's going to represent a box. Okay, I'm going to have what force is acting on that object? Gravity. The force of the force of gravity. What else do I have? Okay, I have the force of the rope, which I'm going to begin to call it T for tension to make things simpler. Okay.
It's hanging?
It's hanging from the ceiling.
Okay.
This is the ceiling. The box is hanging from the ceiling. Okay? So it's got a force down and a tension up, assuming the box is suspended free, but it's not moving. Okay? Clear? Okay. Now, let's do another free body diagram around the ceiling, right there where the rope is hanging. Okay? And let's simplify that by making it some sort of, section of the ceiling like this. Okay? What forces do I have? Yes, ma'am. FBD, free body diagram, right? What forces do I have on the ceiling, the section of the ceiling? I have the force of the rope, okay, and it's called, and we're going to call this tension, okay, and we're going to discuss this in a second. What else do I have? Well, okay, let's assume the ceiling is massless. So that we're not going to worry, or it's so insignificant we won't worry about that. But we have what? We have a normal force, some sort of normal force or reaction force going up. Okay? Is the ceiling moving? Is the box moving? Okay? So that means that my sum of my forces in the y are equal to what? If the box is not moving, what's the sum of the forces in the y direction? Everyone with me? Okay, questions? Okay, some of the forces in the y direction, in the vertical direction, if the box is not moving, this object is not moving, what's the sum of the forces going to have to equal, guys? 0, right? Because it's equal to mass times acceleration. And when I do the sum of the forces, I'm literally just adding up my variables. So what are my variables that I'm adding up on this object, in this free body diagram? Yeah, the T plus Fg, right? Everyone clear on that? Let's do the sum of the forces in the y here. The sum of the forces in the y here. Is my ceiling moving? No, so they're equal to what? 0. And so what are the forces that I have on the ceiling? Normal force plus T. Okay, here's the thing. I'm going to do one more free body diagram. We won't ever do this again, but I'm doing it just to show you. I'm going to do a free body diagram. This is going to be number 3. FBD3. This is the section of the rope in the middle. Okay? Huh? Yeah. This is trying to help you understand why tension is what it is. What's the force coming down? If this is a section right here, right? The force coming down this rope should be equal to what?
Force going up.
Not value-wise, but what is, given the variables that we have, what is the force coming down the side of the rope? This little section.
Do you want to start with the variables, or what is it equal to?
Give me the variable. What is it?
The gravity.
It's equal to V, but right now it's just equal to T, right? Tension, okay? And there must be what up here? Tension. Because if I erase this, if I cut the rope, there's obviously tension going down and tension going up, right? Do you guys see that? And no matter where I cut it, or how big the cut is, it's always going to be the same. So what that means is that anywhere within the rope, the internal forces are always the same, no matter what the rope is doing. If the rope is going around and around and around, but I'm pulling on it, the tension in the rope is always the same. It's always T. Okay, this is important. Does that make sense? Because I can cut, because obviously if I'm cutting it here, I'm cutting it there, I'm always going to have that tension, right? Okay. So, and the reason being is I can start to link my problem with my tension in my rope. So let's look at this. What is the F of G for this 10 kilogram mass? What is the F of G for the 10 kilogram mass? How do I determine that? Okay, it equals mass times acceleration, right? So what's its mass? 10 kilograms. What's its acceleration? Negative 10 meters per second squared. Beautiful. And F of G, the F of G is what's another name for F of G?
Gravity.
The force due to gravity is called weight. Another name for it is its weight. Don't forget that. Okay? So that means my F of G is equal to what? Negative what? I'm sorry? Newtons, guys. Newtons. Kilograms times meters per second is newtons. Right, guys, if you didn't write F equals MA, newtons equals kilograms times meters per second squared, do that. I've done that before, right?
Yeah.
Okay, do you want me to do it again?
It's okay.
Okay. So it's negative 100. What's my units? Newtons. If it's kilograms times meters per second squared. Does that make sense?
So it's negative, it's going down.
Negative, all the negative is the direction, right? So look, so now I can say 0 equals T. I don't know what T is yet, but I do know F of G, minus 100 newtons. So therefore, T is equal to what? So I plug in my F of G is equal to 100 newtons. Okay? Now you're saying, Mr. A, you're making this really simple problem complex. I am on purpose because I'm showing you the construct of how to do a very complex problem with this very basic problem. Do you understand what I did here? Yes, the rope is obviously going to be 100 newtons up. The tension of the rope is going to be 100 newtons because the weight's 100 newtons. We can see that. But I want you to see the mathematical process and how I did that. Because not all of your problems are going to be this simple. Guaranteed none of your problems are going to be this simple. Okay? But do you understand how I got here? Paulina, do you understand? Are there any questions whatsoever? Guys, it's important to ask questions. There are no dumb questions. And if you have questions and you're embarrassed, you can come see me after class, but don't wait.
What class is this again?
What class is this? Okay. All right, I see what you're
No dumb questions.
No, I didn't understand what you meant. Now I get it was a joke. This is history. This is history. Okay. So now that I figured out T, look at this. I figured out T, I can plug it into this T, can't I? So now I can say F of N, 0 equals F of N plus, now on this scenario over here with this free body diagram, what's the direction of T, negative or positive? In this free body diagram here, the negative, so it's plus negative 100 newtons. So that means F of N is equal to what? 100 newtons, upward. Do you guys see that? Do you understand? You guys following the logic? Logic? Logic?
So wait a minute.
Yep. Yep.
And the tension of the box is going.
No, there's no tension in the box. It's tension in the rope.
Yeah. Okay. So that's going up, right?
Well, wait. Depends on which free body diagram are you talking about? On number 1, the tension of the rope is going up.
Yes, and then on number 2,
The tension's going down.
The rope is going down.
Because it's a rope. Because if I'm pulling a rope and you're pulling on the rope, we're pulling in opposite directions.
Yeah.
Right? The same tension. You're having to pull with the same force as I'm pulling.
Yeah.
Right? But you're going in the negative way versus me, or I'm going negative versus you. Right? That's why.
So
Where are you, Karen?
No, I mean, I understand that. I was going to say, like,
Say it.
no, well, because technically, like, if you put the free body diagram 2 over the 1, then the arrows are pointing in the same direction, which is technically compression.
Correct. Where in which way? In
Like,
well, here there's no. In this case, we cut it. There's no rope in the middle here, in the middle. So I'm pulling down here and pulling up there because what I did was I cut this guy out.
Yeah.
And that's where, so there's still, we're pulling against the rope. But on the other side of the rope, there must be that tension there. And on the other side of the rope, there must be that tension there. Right? You follow me?
Yeah.
Hold on. Carmen's got a question first. Hold on. Yes, Carmen.
Okay, I'm just confused on like how the 100 tension like went to negative 100.
Okay. It's just direction.
Oh,
So I look at each free body diagram. Here T is in what direction? Up or down?
Up.
So what's on positive? What about here?
Negative.
Negative, because we're looking. I know I've switched it, but you follow me?
Okay, yeah.
Yeah.
Okay, does it matter if we say FT or T?
Doesn't. It doesn't matter what you say. You can call it FP pink elephant if you want. I'm using 10. I use FT just so because we were talking about forces and I didn't want to confuse you. I'm going to use T now because I want to discriminate between. I want to be able to quickly write T because we're going to be using it to solve for something. And I don't want you to confuse between F of G and F of T. I'm just going to use T. Okay? Call it anything you want. But does that make sense? There's no difference.
So this would be completely different if you had not specified that it's not moving.
Correct. If it depends. What kind of if it had a constant velocity, would it be any different? No. If it had acceleration, would it be? Yes. Okay. Good question. All right. I'm going to erase this. Is this cool? All right. We're going to make it just slightly more complicated. Are you ready? But the process is exactly the same. Okay. My pulley. Everyone understands. By the way, I'm sorry. Does everyone understand what a pulley is?
I know what a pulley is.
Sorry, I didn't mean to not go over that. A pulley. Okay, this is a pulley. A pulley, you've seen them before. They look like this, or like that. The purpose of them, it's like a wheel on a bearing, so it spins freely. Technically, they have no friction, even though they do a little bit, right? The rope runs around it, and the idea is I can change the direction of my force. So rather than trying to lift a box by my legs and pick it up and try and get it way up, I can tie a rope, put it through a pulley, and then pull down on the rope without me moving and lift the box up. Does that make sense? So it's changing the direction of my force by using the rope and the wheels.
Doesn't it make it a lot easier too?
In some cases, we'll do the math, okay? And we're gonna.
But you don't have to apply much force.
Sometimes, yeah. And what you do is you end up trading off the amount of force you have to pull versus the length of pull you have to do. So if I'm going to decrease my force, then I have to increase how long I'm pulling. Okay? And we'll talk about that. All right. So, but let's look at this very simple problem. Okay? So I have my pulley. Oops, excuse me. My pulley is hanging from the ceiling. Okay? And I have a rope here. Oops. And I've got a rope here, and I have a rope here. Okay? And let's say I have my box here like this. Okay? And I have my ceiling, I have my floor down here. There's a guy, he's pulling on the rope. Like that. Okay? That was my best person I drew today. There we go. Okay.
That's a really big pulley.
Thank you. And let's have the guy strapped down so he's hung down, okay? All right, now, here's the thing. Let's say I have a 5 kilogram mass, okay? Let's think about what's important. Let's think about what is important to this problem. What do you think, if I'm going to draw a free body diagram, and I'm going to note that in these problems you have to draw multiple free body diagrams. You can't just draw one, you have to draw multiples. You have to draw it around, the way you do this, you draw it around the things that you know and don't know, okay? What are the and you want to draw it around an object. So what are the objects that we have in this problem? We have the pulley, we have the box. What else do we have? The rope and the man and the ceiling, okay, and the floor. Okay. Now, let's do this. Let's think very quickly about this, okay? In this section here, right here, when I look at this, right there, there's a force pulling up and a force pulling down, right? They're the same. We know that that force is the same. Do we know what they are? Not yet, but we know they're the same. Don't make the mistake of going, I know that what they are, even though all you really know is that they're the same.
Wait, how do you know they're the same?
Okay, because if the ceiling isn't moving and the pulley isn't moving, if I do a free body diagram of that, right? Here's my section of my ceiling. Here's my force pulling down from that little anchor. And if the ceiling isn't moving, there's got to be here's a force of the pulley. There's got to be a force of the ceiling, right? And I know that that's equaled out, right? I could do the free body diagram, but unless I am specifically looking for that value, it may not be necessary.
So is that like F and N?
Yes, perpendicular, exactly. The force of the ceiling and the normal force, okay? But it's a normal force of the ceiling, okay? Same thing with the floor, right? I can ask you how much is the floor pulling back on the person, how much is the ceiling pulling back on that post, okay? But so I can do those things if I'm looking for them, okay? But if I ask you how much force is coming up off the pulley, then you may not need to know the ceiling. All you care about is the force coming up off the top of the pulley. Okay? Does that make sense? Okay. So what's the one thing that we know? What's the one thing that we know in this problem? The mass of the box. And therefore, if we know the mass, we know the what?
Force of gravity.
The force of gravity, also known as? The weight. Okay, so that's the one thing we would know, and so we want to make a box around. We want to make a free body diagram boundary around the object that we know. So I'm going to draw a little box. Oops, excuse me, like this. Okay. Now I could have drawn the whole thing here, okay, if I wanted to. But let's not do that. Let's focus on, if you focus on just around the object, it's going to make your life a lot easier, okay? So you draw the free body diagram. So we're going to call this number 1, okay? So free body diagram 1. I also want to draw a box around what? Or a free body diagram boundary around what? Around the pulley. So it's going to be around the pulley like this. What else do I want to draw a free body diagram around? The man. And I'm going to draw it right around his hands. Now, you can do it around the entire person. I'm just going to draw it around his hands. Because I know after the hands, what? If the hands are pulling down, what about the guy? He's pulling down, the floor's going to be pulling on him, so forth, right? So, let's look at the box. If I draw the free body diagram of the box, what should it look like? Should look like a box, right? What are the forces acting on this box? Okay. Force of gravity and the tension of the rope. Now here, I drew the forces that are literally coming out of this boundary box only. Notice the pulley is not in here, so the pulley has nothing to do with this. The only things coming out of this are my gravity and the tension. Does that make sense? This other rope over here isn't in my box just yet. Okay? Okay. FBD2. What's that going to look like?
Is that the pulley?
That's the pulley.
That'd be a circle.
Could do a circle. Okay. What forces do I have coming out of the box around the pulley?
So you have the tension.
Is it just the pulley? Not the rope?
It includes because the rope is coming out. So I've drawn a box just outside of the pulley. Just outside of the pulley.
So the normal force?
Which direction? Going up. So we're going to call this the force of the pulley, or the force of the ceiling, okay? You can call it whatever you want. It is ultimately the normal force on the ceiling, okay?
So can we call it normal?
You can call it Fn if you want. You call it Fc, okay? But note that if I ask you for the normal force in the ceiling, you have to do that step, Okay. What other? Well, I'll do. Don't worry about it. This. Remember how I showed you? You have to do the step where I've got the ceiling. I have the section. I have the section of the ceiling, right? Okay. All right. So what other forces do I have on the pulley? Very important. There's a man inside the box. Is the man inside the box? No. So what forces do I have coming out of what forces? What objects do I have coming out of the box? The rope. Okay. Assume. But okay. Why do you say tension on either side of it? How many ropes do I have coming out of the box? No, I have 2 ropes coming out of the box. It's 2 ends. Okay. So I have a rope here, and this is what? Tension. I have a rope here. This is tension. Do you guys see that? Now, yes, if the pulley weighed something, then I'd have the force of gravity of the pulley. Assume that the force of gravity of the pulley is negligible in this case, so we won't worry about it. Okay? Yeah, it's at the pulley of the and I won't ever do that to you guys. Make it simple. Yes, ma'am.
Do you need to make like the tension T1 and T2 or anything?
Well, let me ask you a question. Considering our last conversation about the rope and the tension of the rope, is the tension in this rope any different than that rope? No. So it's always the same T. It's the same, and this is a very good question. The tension of the rope is the same. Okay? It's always going to be the same because here's the example. Okay? I'm gonna grab this for a second. Okay? Carmen, pull on the side of the rope. Okay? Be right hand each in a second. So pull. Okay? You're pulling as much as I'm pulling, right? Okay, Morgan, hold the middle of the rope. Okay, now I want you to, Morgan, to pull against me. How much tension do you feel now? Less. Okay? Because if the pulley was pinching, then the tensions would be different. Pinching, like how Morgan was grabbing. Like if the pulley was holding onto the rope, then the tension would be different. But because Morgan, put your hand around the rope like this, as if you're touching it, but you're letting it slide between you. Okay? It's sliding between you like a pulley, right? You feel how much tension? You feel the same tension as what I'm pulling, right? Does that make sense? That is why the tension is always the same. I'm listening.
Holding some of the weight of the box. So the person is feeling less tension.
Say it again.
Okay, like the pulley's holding the weight of the box, so the person that's pulling the rope feels less tension.
Well, we're gonna do that. We're gonna do that in about 3 seconds. Cool. Okay. I'm gonna tie my rope so you can my Hold that. Okay. Come over here. Grab hold on that. Hold that. And pull and support by just pull straight down. Okay, so we're pulling down, right? Okay. Now, if I'm doing that, you're pulling a little less, right? Okay, or you're pulling more, you're pulling the same, I'm pulling less. So really, this is just about, it's just about the tension, okay? The tension of the rope is always the same. Does that part make sense? Clear?
So do you have 2 tensions coming out, or do you just...
Well, if I have my box, how many physical... You always do the forces. Each force in your free body diagram comes from a physical object. So I have the rope coming out and the rope coming out. So whatever comes out of that box, that's what I have coming out. You guys see that? So I have how many ends of the rope coming out? 2. So I'm going to mark them. But is the tension in the rope any different on either side? No. Do I know what the tension is just yet? Don't know yet. But I do know that that's that, right? So let's do one more time. This is going to be 3, right? Here's F, B, D, 3. This is my hand. I'm going to represent my hand as a circle. What's coming up out of that box?
The rope.
The rope. So that's going to be what?
Tension.
T. What's going down?
The
No.
force.
What?
Manual.
The manual for the force of the man, right? Does that make sense? Pulling down. Yeah? All of my forces in this problem are vertical. All of them are vertical. It's important. Okay. So now we write an equation. What equation do we write? Okay, the sum of the forces in the y. Sum of the forces in the y. If for free body diagram 1, I'm looking at the object, the weighted 5 kilogram object. So is the object moving? Assuming it's not moving. So what is my sum of my forces equal? 0. What now, my equation, what are the forces that I'm adding up? T plus FG.
So you can't just add them all up. Like,
You only get the sum of the forces for each free body diagram because that's all you know. You're setting up a graphical model and a mathematical model. Okay? Okay. What about this one here? Some of my forces around the pulley in the y direction. What are they equal?
T plus F.
But initially they equal what? 0. Why do they equal 0? Because it's not moving. Okay, very important. So that's because the pulley's not moving vertically, right? Okay. So now what are my forces here? What am T plus FC. You can do 2T, but I'm just going to leave them as, you can definitely do 2T, but I'm just going to put both T's as you see it. Now, some of the forces in my Y about my person, what are my if my hand isn't moving, what's the sum of the forces equal? 0. What are my two forces? T plus FM. Now notice, in each scenario, my T is in different orientations or different directions, right? So what does FG equal? What is FG? First off, let me ask you a question. What is the only thing I actually know? The mass. And therefore I can figure out the weight or force of gravity. So the force of gravity is equal to what? Negative 50 newtons. How did you get that? 5 kilograms times negative 10 meters per second squared. Okay? All right. So that means that 0 equals what? T plus negative 50 newtons. FG, force of gravity, or weight. So I said T plus negative 50 equals 0, right? So what does T equal? 50 newtons. Is this T the same as these two T's in the next one? Yeah. So now you say 0 equals 2T times 50 is what? Yeah, and it's negative, right? So negative 100 newtons. Does everyone see where I got that? So if I put T in 50 newtons into here, but in this case T is negative, right? So it's negative 50 plus negative 50 is negative 100. Right? Everyone see that? You guys see that? Okay. So this is T is 50. T in this case T is pulling up, right? In this case T is pulling down.
I just need you to repeat what you just said about 50.
Okay. So if this is T is 50, right? But these are pulling down, so it's negative 50 plus negative 50, negative 100. Okay. All right. All right. Plus what? Plus what? F of the ceiling. So F of my ceiling is equal to what?
Negative 100.
Positive 100. Now look at that. That's interesting. How much is the weight of my box? How much is the weight of my box? The weight of my box is how much? The weight of the box is how much?
Sorry. 5.
Is 50 newtons. Why is the ceiling having to pull back twice as much?
Because it's holding the pulleys together.
But why is the ceiling? Okay. Here's a physical scenario. Okay. All right. Here's what I want you to do. All right. Stand up. Stand up. Hold that. Hold. I want you to hold that rope. Okay. I'm going to pull down with a certain amount of force. You feel that force? Just resist it. Okay. Resist it. now, I'm going to put this through. I want you to hold it vertically, okay? Okay, hold that rope. Okay? There you go. Now resist my force. Resist my force. Okay, resist my force. Resist it. Resist it. Resist it. How much do you feel? Is it more?
Yeah.
It's much more, isn't it? It's because we're both pulling down. Okay, that's a really important thing to understand. That because the ceiling has to support the weight of the box plus me pulling on the box. So it's twice. Does everyone see that? Everyone clear on that? You guys clear on that? Okay. Okay. But here's mathematically how you do it. Okay? And now that means that, okay, so now if I look at this, I can figure how much am I pulling? Well, what's my T? 50, is it up or down? In this case, it's up, right? So 0 equals 50 newtons plus my force of the man. So the force of the man must be doing what? Negative 50 newtons, right? So it's pulling down 50 newtons. And that makes sense. I've got to pull down how much weight as it's pulling on the other side. But the ceiling has to do more work. The ceiling has to do more work. Everyone clear on that? It's important. Okay. Let me ask you a question. At this point in the game, I'm doing everything vertically. Okay? What if, though, instead of pulling down, what if I changed directions? Okay? And I pulled this way. I'm sorry?
I don't know, I'm just like, wouldn't you have to pull more? Like, if you would have had to pull more, would the ceiling pull less as much as
Wouldn't it be the same?
down?
Well, let's think about this. How much weight am I lifting here? 50 newtons. How much tension is in the rope? So how much do I have to pull on this side? So whether I'm pulling down or on the side, the same force is 50 newtons. Does that make sense? That's the idea about pulling. I can change the direction of my force, not change the amount of force that I have to pull. But the difference is this. How much now, vertically, how much is the ceiling having to pull against the pulley now, vertically? Only 50, not 100. Only one of those. Because I am no longer pulling down anymore. Do you guys see that? Okay, everyone clear? Yes, ma'am.
So if you were like solving it, you would do all of the sigma Fy and then you would just leave like Fx.
Then you have to do because the forces are in different directions, you'd have to then do a separate thing for F of x. Because at the end of the day, realistically, if I'm pulling sideways, what does this support structure now have to support? Both vertically and horizontally. So you have to calculate how much you're pulling this way to say how much does this mechanism have to support the horizontal force. Does that make sense? And let's say, rather than doing that, let's say we had a force this direction. Now what? What would you have to do? That won't make you ever do this, but
Like horizontal and vertical?
yeah, you'd have to do what?
Oh, so just so that
Yeah, and break it down to its components. Does that make sense? I won't ask you to do it. I won't ask you to do it. But does that make sense? Okay.
Does it matter if it's a parallel and perpendicular kind of, like the rope being perpendicular, like vertically? If the rope's perpendicular to the ceiling, is it more versus like if it's parallel, if it's less?
The tension never changes, but the amount of reaction force each component has to deal with does. Because when I look at this free body diagram for the pulley, it's coming out at an angle. So some of it's horizontal, some of it's vertical. The more parallel, the more horizontal that is, the more I'm dealing with my horizontal force and less of my vertical force. And the other opposite is also true. Does that make sense? But you use the SOHCAHTOA to figure out how much.
Yeah. But like what I'm saying, like I don't know, like finding how much the ceiling has to
Hold.
hold.
Mm-hmm.
Could you like
Well, you have to worry about the ceiling. You have to worry about the direction of force you have to resist. So in the first case, when I was pulling straight down with the person, the ceiling only had to deal with vertical forces. If I'm pulling at an angle or sideways, now the ceiling has to deal with vertical and horizontal forces.
But from horizontal, wouldn't it just be horizontal forces?
But you also have the weight of the box pulling down.
Oh.
You follow me? Right? Does that make sense, everyone?
Is it possible to make all of this just one free body diagram?
Yes. The problem is then you encapsulate everything and you don't know what's going on. Right? The problem is, I mean, let's do that. Let's do that. You could do it. You want to make sure if you do that you're doing it correctly. Okay? I'm gonna redraw this, and let's do exactly that. Watch this. Ready? It's a very good question. Here's this original problem, right? Okay. Let's say that I did a free body diagram, and I'm going to do it in a different color so we can clearly see what's going on. I'm going to make a free body diagram. Oops, excuse me. I'm going to do here. Okay? Does that make sense? I'm sorry?
So you're not putting my hand.
I'm not even putting the guy in it. Okay? I'm going to get rid of all of this. Okay? I'm going to call this free body diagram orange. Okay? So now I have some block. What's coming out the top? Here's my free body diagram. Here's my boundary area. What's coming out of the top of it? Out of the top. This guy here, right? The force of the ceiling. What's coming out the bottom? I've got force of gravity and what? And tension. Okay? The problem is...
Wait, I thought we didn't do gravity for the last time.
No, we did it. We did it.
Oh, this is the box.
This is now a new box.
This is the whole
Oh, I
thing.
thought we were starting with the pulley.
No, now I'm doing... Because she was asking... Because Lauren was asking, what if I just drew a box around everything? The problem is this. Now, I have some of my forces in the y. That's F of G plus FC plus T. Can't solve it. And you only have the one thing to deal with. Does that make sense? That's the issue. That's why you have to pick. Look, you can totally make that boundary anywhere you want. And this is systematically correct. Like it is a correct way to set up a problem. The problem is it doesn't get you anywhere. You follow me? And that's why I'm saying set them up around each object. I mean, look, I could do another free body diagram. Okay, around this. Okay, let's do it this way. Okay, so FBD in blue. So what's coming out my top of my box? FC. What's coming out the bottom of my box? And? Well, I know that FC, so the sum of the forces in the y are equal to 0, which is equal to FC plus 2t, right? So FC is equal to the opposite of 2t. Now that is correct. That is correct. And we know that because we knew it, right? Our forces, whatever the tension was, which was 50, our force up was twice the amount. And that's great, and it still works. The problem is we just don't know what t is. You follow me? So you can set up correct relationships, but you can't sometimes get to where you need to go.
So this is the first.
Well, finish. You can ask me.
The original problem was assuming that the pulley didn't have any weight.
Right. All of these we're going to assume the pulley has no weight.
Okay.
Yeah. Cool?